All are welcome to Physics World, My World. Laser, light amplification by stimulated emission of radiation. The first successful operation of a laser device was demonstrated by Theodor Maiman in 1960 using a ruby crystal. Characteristics of laser light: spatial and temporal coherence, monochromatic, high directionality, high power and tight focusing. Einstein coefficient. Let us consider an atom having two states where N1 and N2 be the number of atoms in states 1 and 2 respectively, and E1 and E2 be the corresponding energy levels. An atom in the lower energy level can absorb radiation and get excited to the level E2. This excitation process can occur only in the presence of radiation. The rate of absorption depends on the density of radiation at the particular frequency corresponding to energy separation of the two levels. Thus, E2 minus E1 equal to H cross omega. Absorption process depends on the energy density of radiation at frequency omega. U and U of omega is denoted by energy density. U of omega d omega equal to radiation energy per unit volume within the frequency interval omega and omega plus d omega. Rate of absorption proportional to N1 and U of omega. Number of absorptions per unit volume per unit time equal to N1 B1 to U of omega. Let us consider the reverse process, namely the emission of radiation at a frequency omega when the atom de-excites from the level E2 to E1. De-excitation occurs through spontaneous emission and stimulated emission. In spontaneous emission, the probability per unit time of the atom making a downward transition depends only on a level involved in the transition, that is dN2 by dt equal to minus H1 N2 is equal to minus N2 by TSP. A21 is known as Einstein A coefficient. In stimulated emission, number of emission per unit volume per unit time equal to N2 B1 to U of omega. It depends on number of particles N2 and density of radiation having frequency omega. B21 and B12 are known as Einstein B coefficients. At thermal equilibrium, the number of upward transition must be equal to downward transition. Thus, N1 B12 U of omega equal to N2 A21 plus N2 B21 U of omega, or U of omega equal to A21 by N1 by N2 B12 minus B21. According to Boltzmann's law, at thermal equilibrium, N1 by N2 equal to exponential E2 minus E1 by kBt is equal to exponential x cross omega by kBt, where kBt is the Boltzmann constant. U of omega equal to A21 by B12 exponential h cross omega by kBt minus B21. At thermal equilibrium, radiation density is given by Planck's law. So, U of omega equal to h cross omega cube N0 cube by pi square c cube into 1 by e raised to h cross by kBt minus 1. Comparing equations of U of omega, we get V12 equal to B21 equal to B and A21 by B21 equal to h cross omega cube N0 cube by pi square c cube. This equation gives the relation between Einstein A and B coefficient. It is clear from the equation that for higher frequencies, laser action is difficult. That means stimulated emission is difficult. Reference: Optics and Gigatic.